Sorry, just sorting out the Zoom stuff. So I'm going to talk about developing spatially balanced occupancy surveys using something called Halton points. Just to give you some background, so my role is really as a consulting statistician for the PAWS project, and mainly based around survey design for camera trap surveys for spatial capture recapture. But we've been doing some occupancy survey, well, helping with some occupancy surveys as part of that, and sort of discovering the close links between occupancy surveys and SCR surveys, and particularly how occupancy can inform SCR surveys. So just some background, the PAWS process, the way that we've kind of conceived it, is as this two-step or two-stage process when it comes to the survey design. And this will carry over to occupancy modeling in other contexts as well. And the idea is that when we've got a really massive area to survey, we've got no chance at all of covering the entire area. So the first step, or the first stage in this two-step process, is basically deciding on survey areas. So in the map that's on the slide, that's kind of like choosing where to put these red dots down. Each of these red dots, it will be tens of thousands of square kilometers. So in themselves, they're very large areas, but they're a very small proportion of the entire area. And so that's the kind of the first, what we call the macro level decision, is, well, where do we go in the first place? What are our survey areas going to be? The second stage is then, like I say, within each of these red dots, how are we going to set up an individual survey? So if we're talking about camera traps, where are we going to put the cameras in this area? So if I blow up this area, it will look something like this. Like I say, it's several thousand square kilometers, and so we need to decide where in that landscape we're going to put cameras, and that's the micro level decision. So we start off by saying, what are our survey areas, and then we go into a more detailed process where we say where are we going to put cameras, or where are we going to do more micro level surveys within each of these survey areas. So then the methodology that we've got at the macro level are these Halton points, and basically a Halton point, I'll talk a lot more about this throughout the presentation, but basically it's a way of evenly distributing those red points throughout space. So it's kind of like putting down a grid, but the key advantage of a Halton point is that you don't need to know how many points you've got in advance. So with a grid, you have to know, I'm going to put down a grid of 9 or 16 or 25 points or whatever, and I can then spread out the points knowing the initial number that I've got. With Halton points, you don't need to know that, so you don't need to know your survey effort in advance, and that's a huge benefit for snow leopard surveys when these things are happening over years and they're very time and resource dependent. So that's at the macro level. That's what I'm going to spend the kind of the next 45 minutes or so talking about. On the micro level, just to say, we've got some optimization routines that for camera trap surveys that basically try and place cameras in optimal areas, and that's to try and get as many detections as possible without biasing, without putting the cameras in areas that would bias the results. I won't say anything more about that because that's not the kind of the focus for occupancy or for today's session. So this process was developed for spatial capture recapture with camera traps, but like I say, there's lots of overlap with occupancy, and so a lot of the principles apply to both. So just to outline what I'll talk about today, I'm going to start by kind of taking a step back and just looking at some basic principles or the foundations of survey designs. So these are kind of useful no matter what kind of survey you're doing. There might be some overlap with some of the material in some of the earlier sessions, but not too much, I hope. And I think it's useful just to recap some of the basic ideas behind like possible pitfalls that you can fall into with any kind of survey design. Then I'll look specifically at spatial designs and the idea of getting a well-balanced design, what this means to have a spatially well-balanced design, and how you use Halton points to achieve this. And then the last part of the session, I'll demonstrate some software that can help you with planning surveys using Halton points. I should say that at any stage, I can't see the chat, but at any stage, if you have any questions, please, actually, okay, I've made it so I can see the chat. So if you've got any questions, just put them in the chat and we'll try and answer them as they come up. Or leave them to the end if you prefer, whatever you prefer. But I'm happy to take questions as we go. Okay, so the basic idea with survey design, as you'll know by now, but it's worth kind of restating, is basically we want to estimate something. So we've got something in mind with occupancy. It's that we want to assess the presence absence of a species in a cell. For other kinds of surveys, it could be other things like abundance. We need to start by defining a survey region, and that's the area that we want to make inferences about. And then the goal of survey design is basically to say, where should we go and sample in this big area that we can't sample exhaustively? So we've got no chance of going and looking in the whole area. So how do we choose the smaller part of the region that we're going to actually put our effort into and then extrapolate to the larger area? So I'm going to use this running example just to demonstrate some of the key ideas. This isn't necessarily this isn't an occupancy example, but we can think of it in occupancy terms. I'll explain that a little bit later on. But the principles in this example carry over equally to occupancy either way. So imagine you've got 51 fields arranged next to each other in a kind of a horizontal line. And each of these fields has got a certain number of animals in them. So the first field has got 8 animals in it. The second field has got 11 animals in it. The third field has got 18 animals in it, and so on. Now, we don't know any of these numbers. So you'll see as we go from left to right that we start with small numbers and we end with big numbers. Let's pretend we don't know that at all. We don't know the total. We don't know how many animals are in each of these fields. So we know nothing. What we'd like to estimate is the total number of animals across all 51 fields. And I'll remind you a few times, but the true number is 2,429. So basic principle of sampling, we can't go and look in every single field and just count up how many they are. So we imagine we can only visit 6 of the plots, 6 of the fields. We'll go to each of those 6 fields that we choose and we'll observe with perfect detection how many animals are there. And from those 6 numbers, we want to come up with an estimate of the total. So that's the task that we're kind of setting for ourselves. Here I've just arranged that data in a slightly different graphical way, so you can clearly see that there's a trend as you go from left to right. The animals become more populous, so there are more animals in the right-hand fields than in the left-hand fields. Okay, so how can we do this? The simplest way is to take a simple random sample. So this is just to say we've got 51 plots. Let's just take 6 at random, and imagine that we gather we choose these 6 that are indicated in green. Okay, so in the first plot that we go and sample, we see 18 animals. The second we see 30. The third we see 29, and so on. So if we add up all of those numbers, we get to 273. So here I'm going to make a really simple point, but that's not, I don't want to insult, I'm not insulting anyone's intelligence. And just, it's useful to try and break things down into really like fundamental or basic like what's going wrong here, to try and understand what we're trying to do when we go from a sample to an inference on estimates about a population. So if we total up all of these 6 numbers, we get 273. Now, that's obviously way lower than the true number. The true number is 2429. So our sum of the total, or sum of the sample at least, is way too low as an estimate of the population. And so you could think, well, why is that? And the obvious answer is because we've only sampled 6 plots. We know that there are 51 of these fields, and we've only gone and sampled 6 of them. So we know, and that's why I say it's a really simple point. We basically can't just add up these 6 numbers and expect to get a good estimate of the total. This number here needs to be upweighted by some amount. And another way of saying that is that each of these numbers, each of the sample total, the number of animals in each field needs to be upweighted by a certain amount. So then we can think, well, what is that amount that it needs to be upweighted by? Well, clearly we have 51 plots, and we're going to sample 6 of them. So each of these 6 plots that we've sampled has got a certain probability of being selected. And that probability is 6 out of 51, because we've done a simple random sample. We've got 51 plots. We've chosen 6, and we've done it totally at random. So each plot has a 6 out of 51 chance of being selected. So what we'll end up doing is upweighting each of these numbers by its probability of being included in the sample, 6 out of 51. That's exactly the same thing as taking this total and upweighting it by dividing by 6 over 51. But I think it's useful just to break it down into these individual steps. If we do that, we'll end up with this total, which is much closer to the true number. So this is our estimate of the population total from these 6 plots. The reason why it's useful to break this up is because we don't always have equal inclusion probabilities. So we might be more likely to select certain fields than others, and we can just simply replace these probabilities with the respective inclusion probabilities if these differ. So that's why I broke these up. So the key point here is, for this kind of estimation that we're doing in this slide, what we need to know is that there's been some appropriate randomization. So we've chosen sites at random. That doesn't mean it has to be simple random sampling, but there has to be some randomization, so that if we did another survey, we wouldn't choose exactly the same plots. And we wouldn't know which plots were being sampled in advance. So there's some element of randomness. And the second thing is that we need to know the probability that each field is going to be included in our sample, and that's called an inclusion probability. So we need randomness and we need inclusion probabilities for this type of design-based inference. Now, I should say we don't actually do this ever in occupancy modeling, because what we'll end up doing is building a model, but it's useful, I think, as a way of just saying this is one type of sampling that we can do. So what this means is that if we choose another sample of 6 fields, we'll get six different fields and a different answer. So here, if we add up the numbers for these 6 plots and divide by 6 over 51, we get an estimate of 2,406 animals. And if we do it again, we get a different estimate. Notice here that in this case, just by chance alone, we've chosen a bunch of fields that have got a lot of animals in them. And that's just unlucky. So because of the randomness in the sample selection, we might land up with an estimate that's quite wrong. And that just means that there's going to be quite a lot of variability in our estimate. So what I did is repeat this procedure. I've done it 3 times here, kind of by hand, but did this 1,000 times, and here plotted the estimated total for each of the 1,000 simple random samples. The true number is in red. That's the 2429, and the mean of the 1,000 samples is in this dashed gray line, which you might not be able to see because it's sitting right on top of the red line. So all that's saying is that our estimate is unbiased from a simple random sample. But notice that there's a lot of variability. So estimates go from around about 1,500 all the way up to 3,500 if you exclude just these bits right in the tail. So we don't know yet if that's a lot of variability or a lot, but it sounds like quite a lot. But remember, we're only sampling 6 out of 51. We're only sampling 6 sites, so things are going to be variable. That variance will go down if we increase the number of plots. So variance goes down with sample size. That's kind of a fundamental rule. Okay, so key points here. In design-based inference, we get variability from the design. So it's the design that provides, that's doing the work, that provides so our estimates are variable because our design is variable. The design, for this whole thing to work, you need a probability sample and you need randomization. A probability sample means for any of the fields that got selected or that didn't get selected, you need to know what was the probability that they would be included in the sample. Simple random sampling is one way to do it, where each field has equal chance of being selected, but it doesn't have to be equal, and there are other ways to come up with those probabilities. Stratification is another option that we'll look at in a second. So if I come back to this kind of bias, do I have? No, I don't have it. Let me go back to this slide. So sampling in favorable areas will bias estimates. So for example, if we go out and look in fields that are where we know animals are more likely to be, say if we have some inkling that the fields on the right are more well populated, of course we're going to bias our estimates. So we choose ones that are choose sites where animals are more likely to be, and then we treat the sample as totally random. Because we're treating all the fields as equally well populated, we're going to land up with an estimate that's way too high. And so all that's saying is that if we sample in favorable areas and treat those as random, it will bias estimates. And that's an important point to keep in mind when designing any kind of survey to monitor the snow leopard populations. Okay, so that's the simplest kind of sampling you can do. So let's try and get that variance down a little bit. And one way of doing that is by stratifying the sample or stratifying the survey region. So here, imagine that we don't know that, or we don't know very well that there's this trend as you go from left to right, but suppose we have some kind of an idea that it might be there. And so we think, well, maybe there is kind of a low density area towards the left-hand side of this survey region, and then a medium density area and a higher density area. So what we might do is to take these 51 plots and divide them into 3 strata. So the first 17 fields make up the low stratum, the next 17 fields make up the medium stratum, and then the rightmost 17 plots make up the high density stratum. And then what we can do is to sample in each of these strata and then put together, so estimate the total number of animals within each of the low, medium, and high density strata, and then put those together into a final estimate. So we want to come up with, we want 6 sites in total. So we've got 3 stratum, and that means we're going to choose 2 sites at random from each of the strata. So say out of these 17 sites, we land up choosing at random these 2 fields. So this is a useful kind of exercise here, just to see if you've understood things. You could think about how you're going to come up with an estimate for how many animals are in these 17 fields. So how many animals are in the low density stratum? Well, we've got our estimate. So we've got 15 animals in this field and 29 in this field. So that's 44 in total. So remember, that's going to be way too low because we've only sampled 2 out of 17 fields. And so we need to take that 15 plus 29, so 44, and divide it by the inclusion probability, 2 out of 17. So we could take 15 over 2 over 17 plus 29 over 2 over 17, and that will give you 374. And we can do the same thing in each of these, in the medium density stratum and the high density stratum. In the medium, our estimate in the medium density stratum is 833, and on the high density stratum it's 1207. So here we have an estimate for how many animals are in each of these low, medium, and high density stratums, and we simply add those together to get an overall estimate of 2,414. This is the idea behind stratified random sampling. If stuff is still random, our sampling is still random. So if we did another sample, we'd get a different set of plots and a different estimate. And notice that here we've chosen 2 plots that are really towards the high end of the low stratum, but that can be compensated for by stuff in what happens in other strata. And so as a result, if I do this 1,000 times and plot the distribution of estimates, you'll see that it's way less variable. So here's the histogram of estimates from simple random sampling in gray, and I've plotted in blue the estimates from the stratified random sampling. There's way smaller variance in our estimates from the stratification process. So this is a really useful technique for coming up with more precise estimates. And often you'll have some idea of where your favorable habitat is and your unfavorable habitat is. A really important point is that you still need to sample the low density areas. So for example, here, we've put the same amount of effort into the low density area as we have into the high density area. We've sampled 2 sites at both. That doesn't have to be the case. So for example, we could have sampled 3 sites here and only 1 site here. So only 1 low density site and 3 high density sites, but we have to sample sites from low, medium, and high. That's really critical for the whole thing to work. The other important point is that the stratification doesn't have to work. So in the sense that our guesses about how to stratify the survey region don't have to be accurate. So for example, if we thought that these were low, medium, and high density areas, but actually it turns out that there was no spatial pattern, we wouldn't lose anything. We'd just revert back to the simple random sampling case. So you don't need to be worried or scared about making a judgment about stratified sampling. If your guesses about what are favorable or unfavorable habitats, or how you'd like to stratify, whatever variable you'd like to stratify on is wrong, or the only way that you pay for that is in increased variance in the estimates and tending towards what you get if you just treated the whole area as a single stratum. Okay, so the key points here are stratified sampling divides up the survey area into subregions. For it to work, it relies on responses within strata being more similar than responses in different strata. You get more precise estimates if your strata are well chosen. If they're not well chosen, you just land up with what you had with simple random sampling. And although I've used equal efforts in my example, that doesn't have to be the case. And so often with snow leopards, you'd want to put more effort into your high density areas, but you must put some effort into the low density areas or unfavorable areas for occupancy. So that's stratification. So last kind of foundational set of slides, and this is more appropriate, I think, for occupancy modeling. So imagine now that we do know that there's some trend as we go from left to right. So we want to make use of that. So essentially what we want to do is model the number of animals present as a function of horizontal distance, x. So how could we do this? We still need to go out and take a sample. So we could take we could do this with a simple random sample. So we land up with these 6 sites. And then what we do is to fit a model. So here we just fit a simple linear model, which says the number of animals present is a function of horizontal distance. And that basically allows us to predict how many animals are in each of the fields, those that we visited and also those that we didn't visit. And we just add up all of these predictions and come up with an estimate of how many animals there are. Here the estimate is 2414. Obviously the quality of this estimate depends on the quality of the model. And so if we choose different sites, we'll get a different model. Here, with model-based estimates, a really important point is that the uncertainty in our estimates comes from uncertainty in the model, not from uncertainty in our sampling. So with design-based estimates that we looked at to start with, uncertainty in the estimates come because there's randomization in the survey design. And so if we choose another survey, choose another sample, we'll get different estimates, and so there's variation that way. Here, this is just some R output that you might be familiar with. Here, the uncertainty in our estimates come basically from the confidence intervals around our predicted line. So these standard errors in our beta estimates. So we can't just, so with model-based estimates, we don't have to take a random sample, because randomness is not coming in through the sampling, but through the model estimates, through the estimates of the model. So that doesn't mean that we can choose any old fields, though. For example, if we choose these 5 fields, or these 6 fields that are already close together, we might come up with a model that's not very good at all. A useful way to do this, a useful way to sample for model-based inference, and this is kind of going towards spatial sampling, is to equally sample, or sample a gradient of covariate values. So include both low values of the covariate and high values of the covariate. It kind of makes sense to spread those out equally. If we're going to choose 6 points, we can choose six fields spread out from all the way from the left-hand side to the right-hand side. That doesn't guarantee that our model is good, but it means that we've sampled a range of covariate values, and that's normally a good thing. Okay, so here in model-based inference, it's the modeling that does the work, not the design. We don't need a probability sample, so we don't need to randomize the sample, but we can use one. So you can use a simple random sample and then just fit a model. You can't go the other way around, though. If you haven't used a random sample, so if you don't know inclusion probabilities, you can never use a design-based estimate. Our main goal in coming up with a good estimate is developing a good model. And in order to do that, a useful approach is to try and sample the covariate space well. So this is, if you want to model occupancy as a function of ruggedness, for example, you need to sample both highly rugged and less rugged areas. And because occupancy nearly always involves model building for both the detection and the occupancy process, these last sets of slides are really the ones that are relevant, most relevant going forward. So inference is model-based, and so we want to choose our samples so that we sample a range of covariate values and avoiding bias. Okay, so that's kind of gets us neatly into the whole idea behind spatial sampling. So with spatial sampling, we're basically sampling a phenomena like animal density or occupancy, like probability of presence, that varies spatially. And so the idea with spatial stuff is that observations that are close together in space will typically be more similar than observations that are far away in space. And so on the previous slide, my covariate just happened to be a spatial covariate. But so that's why this slide looks pretty much identical to the previous slide. The previous one is more general in that it says if we've got any covariate, we want to sample both high and low values. With spatial sampling, it says if we want to come up with a precise estimate, what we want to do is to spread our samples out in space. And the reason for that is that if you have samples that are very close together, they're going to be correlated, and correlation generally inflates variance. Positive correlation between your sampling units will increase variance. So if we want to do design-based estimates, design-based inference, we need to have some randomization. And the way that you do that in spatial sampling is by choosing a random starting point. So here I've randomly chosen this, that we're going to start in this field. And then the interval between our sampled fields is constant. So if I choose these 6 fields, these 5 fields, I land up with an estimate of 2, 3, 4, 6. If I choose a different random start, I land up with a different estimate, but note that there's not much variability. These are obviously just 2 samples that I've chosen at random, but because the sample is spread out spatially, the variance in its estimate is going to be pretty low. So this is the way that spatial sampling basically works at a foundational level. The idea is that observations close together are going to be correlated. That's bad for variance, so we want to spread out our samples equally across a survey area. That's the idealized case. Obviously, when we're sampling snow leopard territory, you can't just say, okay, well, we're going to go and sample exactly every 10 kilometers. Something might be inaccessible, something might be a village. It's just not possible, but it's useful to keep this kind of the idealized standard in mind when thinking of designing surveys. So how does this work in two dimensions? Up to now, we've just been talking about a single dimension, but obviously we always sample in 2D or sometimes in 3D. So they basically, the principles carry over pretty much directly. So if we've got a survey area that looks something like this, what we do is to chop it up into grid cells and then choose some of those grid cells. So this could be a simple random sample. Here, this is bad because these 3 sites are probably going to be correlated with one another. We prefer to have them spread out. But we can do simple random sampling. We can do, sample according to a grid. This would be a spatially balanced design because it's spread out through space. But we might not, so the disadvantage of this is that firstly, we need to know that we've got 9 points, 9 sites that we're going to go and sample, and we need to know that in advance. If it turns out, for example, that we only land up going to 4 of them, and these are the first 4 sites that we, these are the first 4 sites that we sample, that's not as well balanced as it would be if we had known that we had only going to sample 4 sites to begin with. Then we would have chosen a grid, something like this. So we need to know that there are 9 sites that we're going to survey in advance. And also the survey area needs to be reasonably regular. So if we need to, if we have a highly irregular survey area, so something that's kind of very, very bendy and windy and goes all over the place, but it may not be possible to overlay a grid on top of that survey area. Yeah, we could probably do it with some jiggery, but there might be better ways. And so the idea with the Halton points is basically to say, no matter how many surveys we've done, let's always try and maintain a spatial balance. So this might be the first cell we visit. The second cell we visit is on the other side of the survey area, then the third one, and the fourth one, the fifth one. You'll see that no matter where we are in the process, we've kind of got an even spread of points throughout the survey area. Okay, so so that's spatial. Those are 3 different ways of doing spatial sampling in three dimensions. Simple random sampling you probably wouldn't want to do. Grids are excellent if you can use them and you know your survey effort in advance. Halton points are good when you don't have those nice, neat features. Okay, so I'll talk for a bit now about Halton points in a little bit more detail, and I've kind of mentioned them a lot, but I'll explain them in detail. So there's Costa mentioned balanced acceptance sampling, which is a way of doing sampling with Halton points. So balanced acceptance sampling uses Halton points. I'd kind of use those two terms interchangeably. On the Google group, I'll after the session, I'll put up a paper which explains balanced acceptance sampling and has some examples in it. So again, we'll start in one dimension just because it's easiest. So imagine you've got this line from 0 to 1. The idea with balanced with Halton points is basically to keep on splitting this interval equally in half, in a way that the points that you've sampled so far are well spaced out in this interval. So the first Halton point is a half. Then the next Halton point splits this first interval 0 to a half in half. So it's a quarter. Then you move over to the other side of our kind of one-dimensional survey area and you split this in half. So the next Halton point is 3/4. Now you've got basically 4 stick lengths, if you like. So the next Halton point goes to this one, the first one, and splits it in half. That's an 1/8. Then goes to the next one, and splits it in half, goes to the next one, splits it in half, and goes to the last one and splits it in half. So we can carry on this procedure infinitely. All the points that we've generated so far are going to basically be evenly spaced in the interval. I just show it in one dimension because it's easier to sort of see that way. This is how it would look like in 2 dimensions, and this starts to build a spatial sample. So I've shown here the first 12 Halton points. The first 6 are in red, and the next 6 are in blue. So you see, it starts. So it starts in this grid cell. Here's a point down here, and then it goes up to this grid cell, then to this grid cell. So it goes here, 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 and then the 4th one comes back down here, 4, 5, 6. So it's kind of like this, you know, a V on its side pattern, and then a V on its side, on its other side pattern. And then you'll see that that's replicated in the next 6. So 7, 8, 9, 10, 11, 12. And so you'll see that if I take the first 6 points, they're well balanced spatially. If you just kind of zoom out or kind of squint your eyes, you can see that they're pretty well distributed in space, not like a grid, but they're pretty even. And the next 6 are also pretty well distributed in space, independently of the first 6. So if I just look at the blue points, they're not amazingly, these are quite close together and these are quite close together, but they're not bad. And if I look at all 12 in combination, they're also pretty well balanced. So this is a property of Halton points, that if you take any sequence of Halton points, the first 6, the next 6, from point 1000 to point 1006, 1005, those points will all be well balanced. So any sequence of Halton points is well balanced, and that gives the sampling procedure its power that you don't need to know in advance. Firstly, well, not firstly, you don't need to know in advance how many points you've got, but it also allows you some element of randomization, because you can decide where in the Halton sequence you want to start. And that's just a randomization procedure. So I could start at point 1, I could start at point 6, I could start at point 1000. That allows me to randomize my sample. So that's quite powerful if you're going to do design-based inference. For occupancy, we won't be doing that, but it's useful to keep in mind. So this is these are the Halton points around from 902 up to 913. Also pretty well spatially balanced. This is the first 100 Halton points, the first 50 in blue and the second 50 in red. So you'll see that as you generate more of these points, it becomes clearer that actually you're getting pretty good spatial coverage throughout the area and things are pretty well balanced. And this will be good for getting low variance estimates. What we can also do, so this design that I've done so far is just a really regular square survey area, but obviously most survey areas aren't like that, but that's perfectly fine for Halton points. Because any sequence is well balanced, it means that if we're not allowed to sample in the survey area, I just drop if I get a point in this area, I just totally ignore it. I just move on to the next point in the sequence. So I can have a very irregular survey area, and I basically just generate a whole lot of Halton points, and whichever Halton points fall into the areas that I can't go to, I just ignore them. So irregular survey areas are handled in a straightforward way. And I can also do stratified sampling. So say, for example, this green area is has a lot of animals and was favorable habitat, and this blue area is unfavorable habitat with very few animals. I may want to sample more intensively in this area. So what I do is generate Halton points, and I'd put these down one by one until I've got my desired number of samples in this low unfavorable area. And then I just reject any further points that I generate in this area. So I say, okay, I've got whatever it is, 40 samples in the unfavorable habitat. I don't want to do any more. So if a point lands in this blue area, I just ignore it, and I keep on generating points only in this green area. See that within each stratum, so within the blue area, things are well balanced, and within the green area, things are well balanced. So we can do stratification as well, and that's also a useful feature of Halton points. So when to use them, it's more useful to think about when not to use them. The first is if we've got very few points. So if you're only going to choose 3 survey regions or 3 sites to go and sample, I know this wouldn't happen for occupancy, but it might happen at the macro level. If you're only going to choose 3 survey areas, there's not much point in doing using a Halton sequence for this. You could just space these out evenly visually, or using just spatially well balanced. So Halton points are really for when they're more than just a few points. This is especially important if you're doing design-based inference, because you need enough samples to calculate variances, and typically something like 20 sites would be needed. So if you know how many surveys you're going to do, you can use Halton points, but you can also use a grid pretty effectively in most of these, in most cases where you know the number of surveys, unless you have a very irregular survey region. Remember, with occupancy models, you're almost always building a model, and so you want to sample both high and low values of any covariates that you're including in your models, and so that will also dictate where you put your survey points. If your covariate varies sort of smoothly through space, grids become a good option, because they almost automatically sample both high and low values. So then when you'd want to use Halton points is basically when those nice features don't apply. So low coverage means you can't sample the area exhaustively. You don't have covariates that are non-stationary. So say, for example, snow leopards liked high elevation areas in this part of the survey area and low elevation areas in this part of the survey area. That would be an example of a non-stationary covariate. Basically, the effect of the covariate on occupancy probability is different throughout your survey area. In that case, you'd have a problem doing any kind of model-based inference, unless you can stratify. Basically, unless you can include that knowledge into your model. So if you've got a very irregular survey area where grids don't apply, that's a good place for Halton points. And the main one, if you don't know your survey efforts in advance, so you don't know how many points you're going to be able to go and sample now or in the future. So in that case, Halton points are a good option. Okay, so to summarize where we are, so this is the first law of geography: near things are more closely related than distant things. And the idea behind spatial sampling is to exploit that fact, and spatially well-balanced designs do this. Grids and Halton points are both examples of designs with good spatial balance. grids are much more rigid and inflexible, but they're simpler. Halton points are really flexible, can handle just about any survey area and situation, but they're a little bit more complicated to come up with and to work with. So what I'll show you now is an app that we developed to help with generating Halton points. I'll just break out of this and so all of the code that you and data that you would need to do this, I just wanted to say, is available on GitHub at this address. Well, this will be on. It's on the slide, I guess, now. So you can repeat what I'm going to show you now. If you just go and download all of the code from this repository. There's also a cheat sheet which takes you through the process that I'll show you now. And I just wanted to mention, I'll just zoom in here, to say there are 3 different ways to do what I'm going to show you now. The easiest way is you can run this app directly in a web browser by just pasting in this link. This is not the link that I've just shown you. This connects to a server that has the app preloaded onto it. And the advantage of this is that you don't need to have R installed or anything like that. You could just run this directly. The second way is just to run these 2 lines of code. And what this does is basically it loads Shiny and then it runs the app that I've got, that I just showed you in that repository on your computer, but just with a single line. So you don't need to download a whole lot, but you do need to have some packages installed, and that's over here. The other way is to do what I initially said, and that's download that GitHub repository and install it, or just save it to your computer and run it locally on your machine. So there are 3 different ways to run the app, from kind of easy but won't give you a lot of flexibility to will give you a lot of flexibility, but needs you to have packages and are installed. Okay, so let me show you how this works. It's always a little bit nerve-wracking doing a live code demo, but hopefully it will work. Okay, please also shout if there's a long lag. I'm not sure, like if what's showing on my screen is showing on yours. So if what I'm saying makes no sense to what the stuff that you're seeing, just say. So what you should see here is a map centered around Kyrgyzstan and some options on the right. So what we want to do is to load a survey area and basically generate Halton points for that survey area. So there's click on the browse button, and I'll browse to where my data is. And what you need is a shapefile with your survey area. So just the standard, these four extensions are kind of bits and pieces of a shapefile. So you need to highlight all 4 of them and click open. That will then upload the survey area and zoom into it. So this is basically our survey area. You can change the base map, which allows you, and you can do things like zooming in and zooming out. So you can it's an interactive map. You can play around with it, and this will allow you to sort of see the underlying characteristics of your survey area a little bit better than if I just use this map. But this map's a bit quicker, so I'll just leave it on this for now. So this is our survey area, and we want to generate, say we want to generate 20 Halton points. We just say we want to generate 20 points. This is a random seed, and this is basically like the ID for your survey. So remember I said that with the Halton sequence, you can basically start anywhere in the sequence. So you can generate the first 20 Halton points, or you can start at Halton point 1,000. And this allows us to randomize the survey. Well, this is where we set that seed for the random survey. And so it's really important to record the seed, because if you don't record the seed, you won't be able to come back later on and reproduce your points. Any results that get saved from the app automatically have the seed in it, but I think it's useful just to make a note of it somewhere. Okay, so 20 points, and then we just click Add Surveys. And here are our 20 Halton points. So if you hover over the points, you'll see, so this says, I'm not sure if you can see this, but it says this is point 11. So this is the 11th point that we would visit if we were visiting them in order. And it gives you a lat long coordinates for that point. Okay, so say we went out and did these 20, and then we say, okay, we've got money to do another 10. Where should we go? So we put in 10 and click Add Surveys. The points that we've been to turn blue, and the new points are in red. So we did those, and we say, okay, now we get a big whack of money. Now we can go and do 50 more points. These are our next 50 points. Obviously, you don't need to visit these in exactly the order that have been specified. So you don't need to go to point 1 and then point 2 and then point 3. But you just need to remember that the points are designed so that they're well balanced. The sequence of them is well balanced no matter where in the sequence that you stop. So if you generate 20 Halton points, but you only go to 10 points, and you don't go to the first 10 points, you go to any 10 points in the first 20, it may not be that well spatially balanced. So it's useful just to be conservative in the number of points that you generate each time. Okay, so that's the basic usage. Once I've generated my Halton points, at any stage, I can click on this download button, which will download a CSV file with the lat long coordinates of each of these points. Okay, so I'll just demonstrate two more advanced features. The first is what happens if if there's some areas that we've already been to. So some already sampled areas. So I can load in these areas also as a shapefile. And hopefully the resolution is good enough, but you can see that these are areas that we've already been to. Already sampled. So now if we generate, well, we generated 30, then 20, then 50, so we generated 100 in total. If I add those surveys, you'll see that any points that fall into these areas that we've already surveyed will be removed. So basically, we won't go to places that we've already been to. So it allows you some flexibility in generating a design that's spatially well balanced, but that doesn't repeat survey effort. That's the one thing. The other thing that you can do is to do stratification. So here you need a variable in your shapefile to stratify on. That variable needs to have a specific name, and I'd have a look in the cheat sheets for exactly how you would set that up. But basically, there's a variable in your shapefile that's called stratum ID, and that would include your stratification variable. So this is a little bit more complicated. Here we've got we've basically stratified here by occupancy probability. So this green is a low or unfavorable habitat with a low predicted occupancy probability between 0 and 0.33. Orange is medium, 0.32 to 0.66, and blue is high, 0.66 to 0.99. And then these percentages tell you the percentages of all of the cells that fall into each of these strata. So what we can now do is to generate, say, 100 points. Nothing really looks different, right? And the reason for this is that by default, we sample each stratum in proportion to its relative area. So basically 38% of all of our points, so 38 out of 100 points will be in this green area. 39% of all the points, 39 out of the 100 points will be in this orange area, and 23 out of the 100 will be in this blue area. So basically we're sampling each stratum proportional to its area in the whole survey. And so that means that we land up with this even distribution over everything. But that doesn't have to be the case. So I said you might want to put more effort into the most favorable habitat. And so to do that, you can, in this box that says sampling proportions per stratum, say it's in, say I want 10%, 0.1, to come from this low occupancy stratum, 10% to come from the medium, and I actually want to put 80% of my survey efforts into the high occupancy stratum. I click update to load those values in. And now my Halton points are almost exclusively in these blue areas, in the high density, in the high occupancy areas. So basically I'll have 10 out of my 100 points in the green areas, but those will be spatially well balanced within the green area. I'll have 10 points in the orange area, and those will be spatially well balanced in the orange area. And I'll have 80 points in the blue area, and those will be spatially well balanced. Even though if you zoom in a little bit and look at the blue area, you'll see that it's highly fragmented. So doing this with a grid would be really, well, it would be impossible, because this blue area is just totally fragmented. But with Halton points, we can generate an arbitrary number of points, and these will be well balanced within this high occupancy area. Like I say, these last two features, so excluding existing survey areas is pretty standard. Well, not too advanced. That's just means you need to have your shapefile set up. The sampling, the stratified sampling, is a little bit more advanced, and it probably want to be a little bit careful with these proportions. Not as extreme as what I've put in here, for sure. Again, once you finish everything, you can download the survey button. So download the survey points with this button. And just a final reminder to always record this the seed, because if you choose a different seed, you'll get a different set of points.